continue. So this is again the full equation, yeah, and this in particular, if you think about this one being dependent again, just to make that clear, as we have introduced it, being dependent on the number of agents in the minus or plus group, plus there may be complicated transition rates. Yeah, since this might be highly nonlinear and state dependent, the overall evolution equation for the opinion index x with these components on the right-hand side also is highly nonlinear. It's a highly nonlinear system of differential equations that is hard to analyze. And in order to facilitate the analysis, we perform this well-known, in fact, in mathematics and physics, well-known Taylor approximation of second order that leads us to the Fokker-Planck equation. And this assumes that we have a large number of agents and that x then is close to a continuous quantity. X so far was discrete, so that we can perform a Taylor expansion with respect to delta x. We rearrange the master equation in this way, collecting the W ups in the first line and the W downs in the second line, and then we take W up times P as a function and W down times P as another function, and perform a Taylor series expansion with respect to delta x of second order. We replace this discrete evaluation here with a Taylor series expansion.
That would be an indication that it's not a diffusion in general, is it? I mean, for a diffusion, you generally get a second order differential operator in that set.
Yeah.
And in that case, that might be a higher order differential operator which you get. And
it normally is, yeah.
Okay, so then it may not be a diffusion.
But is it a necessary condition to have a second order approximation for diffusion?
A diffusion is always a second order differential operator. I think that's the definition.
Okay, so then it's, yeah, beyond a simple diffusion.
I mean, there are certainly Markov processes
Yeah.
which are not diffusion, so that might be.
Okay, yeah. So what you do now is you approximate it by a diffusion process.
Okay,
you have the diffusion approximation. I come from a somewhat different terminology.
Yeah.
So this is the second order approximation, yeah. You approximate now these functions W up and W down around delta x. Delta x is 1 over n. These are the steps of delta x with a given population size, and therefore we have these first order terms, and second order terms. Second order terms then come with delta x to the square. And now collecting the first order and the second order terms, we get this equation, which is called the Fokker-Planck equation. We have the drift component, and the diffusion component. Fokker-Planck or forward-Kolmogorov equation. You see immediately that the drift component comes with delta x equal to 1 over n, whereas the diffusion component comes with delta x equal to 1 over n squared, which means the diffusion component goes to 0 more quickly than the drift component, and therefore the system for large n converges to a deterministic system. But it's actually not necessarily so, in a sense, because you might have counteracting forces here in the transition rates within the diffusion. And we have studied cases like this. I don't emphasize this in the following, but you can have...
You will carry it in general always up to the arbitrary order. You can expand it up to the arbitrary order, choose, and depending on your transition probability, just offset those terms one time.
And this is an interesting aspect because it tells you something about the importance of the system size, whether certain properties survive this increasing system size or not. We have two terms here, the drift term and the diffusion term. Here I have reproduced them again. And you see that the drift term and the diffusion term both depend in a very simple way on these functions W up and W down, the movement, the transition rate for the system to move to the next higher or next lower value. It's simply the difference between W up and W down that gives you the drift of the system. Yeah? Whether it's more likely, it's quite plausible, whether it's more likely to move to the higher or the lower state gives you the general drift of the system. If the difference is positive, then you have an upward tendency. If this difference is negative, then you have a downward tendency. And the diffusion term is the sum of both because that gives you the volatility of the system, the overall rate of change of the system. A few remarks here. Yeah, as we said, it maintains only systems, it maintains only terms up to second order, but you can go on, and it might be interesting to go beyond the second order term to third order, fourth order. It might be particularly interesting if you have a system with a small number of traders or small number of agents, because then the first order and second order approximation might be relatively unprecise or might be far away from the microscopic behavior of the system. It might be better to go to third, fourth order whatsoever. This is a question that concerns, it's actually an empirical question. Yeah? It concerns the system size. And this is something that economists have seldomly pursued, to ask themselves what an appropriate system size is for a theoretical description of an economic system, say a stock market. How many active agents do you need in a theoretical model in order to describe the qualitative characteristics of a stock market? Here we can get something like an avenue towards an answer to this question that has not been asked before, and that is important. In fact, when we apply this, and hopefully I will have time to come to that later on, when we apply that empirically, we can estimate n. If we don't know much about the number of active agents, we can estimate n. We can estimate the number of active components in the system. How many agents would we need in order to replicate in a theoretical model what we see in the real world? So this is what we see here, second order approximation. So you can do a diffusion approximation of the original jump Markov process. For simple drift and diffusion functions, but mostly we don't have simple functions, you can actually solve for the stationary distribution by simply setting the left-hand side equal to 0. There are standard ways to solve for the stationary distribution, but mostly our systems will be too complicated in order to arrive at some closed-form solutions. And in general, this Fokker-Planck equation can be analyzed and in fact simulated more easily than the master equation. So it's the method of choice for much of what we do in the following. And the n-square dependence of the diffusion term is simply a consequence of the law of large numbers, but it assumes that there are no countervailing forces in the transition rates. If the transition rates are independent of the number of agents, then we have a law of large numbers, but we might have a violation of the law of large numbers if we have particular forms of transition rates. I will show you some examples of the Fokker-Planck equation later on. Before we come to that, the second element here of the underlying apparatus is to say something about the moments, the development of moments over time, and once we have characterized that, we can go into applications. So this pertains, what we have done so far, to the full, complete probability distribution. So what we can get with this Fokker-Planck equation is the change of the probability distribution over time. The change of the probability distribution over time. Maybe I go a bit forward in order to give you simply an idea of what that looks like and what the value of these apparatus, of these formalities could be. The details I give you later on. This is the development of a probability distribution over a state in time, yeah, given a certain system using the Fokker-Planck equation. So this is the time axis, and this gives you the possible values of an opinion index from -1 to 1. Yeah. And here I have the probability density. I start here with an observation at time 0 in the background, yeah, at the start of the time axis. In principle, this observation then I approximate by a sharp normal distribution in order to avoid a delta function, but this is only a technical point. So you see a sharp normal distribution here for the initial observation, and then I keep track of the dynamic evolution of the probabilities. Yeah? And you see the dynamic evolution here of the probabilities as they occur in time over, I don't know, 1, 2, 3, 4 time steps, whatsoever it is here on the time axis. You see that, for example, developing into a bimodal distribution. Yeah, what you can infer from a certain system that I'm going to introduce later on in a moment is that even if you have a balanced state, yeah, x equal to 0, which means as many pluses as minuses in the initial situation, there will be a tendency to move towards a bimodal distribution. That means the most likely observations here at time delta t, if that is my time horizon, the most likely observations here are a strongly positive or a strongly negative majority of my population because of reinforcing mechanisms in the background, probably. I cannot predict, in fact, which one will prevail, but I can predict that my population will most likely be in something like a dominant optimistic or dominant pessimistic state at time delta t. Here it is symmetric, and here I have some asymmetry added, which allows me to tell that, or to predict that the optimistic state will be more likely, because of some exogenous, maybe private information of some individuals, the optimistic majority will be more likely than the pessimistic one. But still, the pessimistic one also has a non-negligible probability to it. And what is least likely, in fact, is to still have a balanced disposition. Yeah. So that will vanish with a high probability and will evolve into an optimistic or pessimistic majority among the population due to certain forces that I have to describe or hypothesis about the behavior of the agents. And to forestall a bit what I would like to show you at the end today, this mechanism can also be used to estimate models, because that gives me the probability of states at time delta t, at the next time. So it gives me the likelihood of the next state that I observe. It is simply something that I can use as the input in a maximum likelihood estimation of a model of interacting agents. Yeah. It's the conditional probability of any observation that I make here, conditional on the previous state of the system, which is represented in my time series. And therefore, that can be used as the input in a maximum likelihood estimation procedure for the parameters of my system.
Why? I mean, the existence of modal distribution means actually the existence of some basin of attractions in the system, right? Because in your mean, your transition probabilities have to have the quadratic inert, say, so that it ensures actually the existence of
they might have different functional forms.
Yeah, and then depending on parameters, you actually over time you can move from one basin of attraction to another one. Right?
Yeah, you can move.
You can
of
move.
course.
And then that's puzzling why we cannot predict, you know, because we can estimate the time for, I mean, average time necessary to move from one to the other, right? So basically,
we can make stochastic predictions, and it depends on parameters, on prediction horizon, and so on the prediction method, how good our predictions will be. One point is that a mean prediction is not very good here. To use the mean as the prediction, which is the natural way to predict, will not give you a very successful prediction. Of course, if you start now at time, say t equal to 1, with an observation of minus 0.6, then it's very likely that you will stay in that negative majority for a certain time. So you would predict for the system that it stays there until the next period, but it depends on the time horizon of your prediction. If your time horizon is very long, then you only know that it will switch occasionally between plus and minus majorities, and then perhaps the mean might be better because you have lost the correlations and you don't know anymore whether it will be the plus or minus majority. So there are quite intricate questions of forecastability of these systems, and we are just starting to explore these topics. So let's go back to our mathematical apparatus. That was the harder part, to characterize the full probability distribution. What besides the full probability distribution we probably also want to have is, and that I have indicated in the introduction, some knowledge about the expected behavior of moments. First moment, second moment, but also higher moments. And this you can get with some efforts from this apparatus as well. If you think about the expectation of x at time t, x bar, then it's given by the sum over all x times the probability density at time t. And its change in time, in fact, you see immediately involves the master equation. The change in time is then the sum over all x times the change of the probability, which is given in its exact form by the master equation. And in general then, by inserting this flow of probability that we had on the right-hand side, you see that you have to compute the sum over all x times the sum over all possible inflow components of probability from other states x prime minus the sum over all possible outflow components of probability into other states x. But in principle, everything here is available, so we have been working with these components before. We can now use these components in order to characterize the time development of the mean value x bar at time t. With a few simple manipulations, you don't have to track that immediately, we get the following. What do I do here? I separate between the first and the second term. We have two sums here, the first and the second one. Then what I can do in the second one is or in the first one, let me check it. Here I change x and x prime because it's the same set of possibilities. I change between x, the summation over x and x prime, so I change a bit the outlook of this, the appearance of this component here, and then it looks pretty much the same like the second component except for x prime and x. So I can recombine it in this way, and then I see what we have here in the center of the expression. In the center of the expression is something which I denote as AX1. It's the average expected jump of the system, from x to some other state x prime, summed up over all x with the weight which is equal to the transition rate. And this is called, in the statistical physics literature, the first jump moment. The first jump moment. So you can trace it back to the expected jump of the system from any state x to another state x prime. And then you still have the outer components here. So taking all these jump possibilities here, you see that you weight them with the probability of the initial state x, which means you get something like the average jump, in fact, of the system, which is intuitively plausible. So it's just a kind of elaboration of the dynamics of x bar. X bar can be traced back to the average, the dynamics of x bar. The change of the mean value can be characterized by the average expected jump of the system, which is absolutely intuitive. This is the first jump moment. And if we look more deeply at it, we see that it coincides with the drift component of the Fokker-Planck equation. The first jump moment is exactly the drift of the Fokker-Planck equation. We just have to insert our formulas for Wx prime x here. It's W up and W down, yeah, because we only have the two possibilities moving to the next higher or next lower state, and taken together, because x prime minus x is 1 over n, or minus 1 over n, taken together, we recover the drift term of the Fokker-Planck equation. So the first jump moment is the drift term of the Fokker-Planck equation, and the drift is in fact, as we know already perhaps, the drift is in fact governing the mean value dynamics. The systematic part of the dynamics. So that's what we get. That's what we get. The change in time of the mean value is given by the expected drift of the system. And this can also be called the first jump moment, because it's the expected jump of the system. But we have derived it, it's worthwhile to emphasize that we have derived it from an exact equation. Yeah? It's an exact expression for the drift, which we only have reformulated in order to make it more manageable. But this, of course, involves all possible states x. So it's not a closed form solution for the drift. It's not a closed form solution because it goes back to the probability distribution over all possible states x. And it would be better and more tractable if we had a closed form solution here. We can get closed form solutions by again performing some approximations. In particular, if we perform a first order approximation, then approximating these complicated, because you have to insert here the expectation of this expression, approximating this complicated first jump moment to first order simply means that I take the function ax1 at x bar. And that immediately leads to a closed form expression. But it's only an approximate law for the mean value dynamics. It's an approximate law. Its accuracy depends on the system characteristics, but at least it should be a good starting point in order to investigate the systematic dynamics of the system. This is exact, in fact, if the first jump moment is linear. Yeah, if this function is linear, then of course we don't have any problem here, and the first order approximation is exact. You can also get a second order approximation. You can go to arbitrary order. Again, as with the Fokker-Planck equation, it depends on the system characteristics, how many terms you would like to maintain. First order gives you this one. Second order, you have the first order component. Then you have the first derivative times x minus x bar. The second derivative times x minus x bar to the square. But you also have the expectation of that one, which means that in expectation this component vanishes, and in expectation this component is equal to the variance, yeah, the second moment, so that you come up in second order approximation with a dynamic equation that has a feedback, and that's quite interesting, that has a feedback from the volatility of the system on to the first order dynamics. In second order, you have a feedback from the variance. We don't know anything so far about the variance, but we will know in a minute. You have a feedback from the variance on to the mean value, which is quite interesting if you think about leverage effects and asymmetry in stock returns. Yeah? You have an immediate access to covering such effects in this framework.
No, but this equation is implicit again, right? Because the sigma x the variance also changes over time.
Changes over time. This is not a closed form solution.
Yeah.
At the moment, we can't do anything with that.
This guy, you could extend that.
We extend it in a moment. And then we have a system covering the mean value and the second moment. Yeah. An approximate system of two dynamic moment equations that gives you information, and we will look at examples later on, gives you information about the first and second moment simultaneously. So at the moment you are perfectly right, we can't do anything with that because we have no information so far about sigma x squared. Yeah? But we see that in the second order approximation we need information about sigma x squared. And you might have interesting effects, interesting spillovers between both moments. Now I show you a simple example just to concretize some of the ideas here. I just applied to simple birth and death dynamics, which you can also apply in industrial economics, birth and death of companies, exit and entry of companies. But just for the sake, so to say, of concretization of what we have done, of illustration of these concepts, I assume a certain population, yeah, n is now simply the number of individuals in a certain species, say, and I have a birth rate, yeah, lambda, which means that any individual can give birth to a new individual in the species with a probability lambda per time. So we have asexual reproduction here. And I have a death rate, which is a bit more interesting here, in that the death rate mu depends also on the number of individuals. That assumes somehow that capital N is something like a maximum carrying capacity of the environment. The death rate increases if the current population N approaches the maximum carrying capacity. So it is state dependent, and of course then it's multiplied with the number of individuals. That's the probability, or the rate, the Poisson rate for death of an individual per infinitesimal time increment in this dynamic process. So a very simple example, constant birth rate and state-dependent death rate because of an overcrowding effect of individuals of a species in a certain environment. And this is something we can analyze with the apparatus that we have developed so far. We can say something about the probability distribution evolving over time. We can say something about the first moment, and later on we will say something about the second moment as well. In fact, just to indicate that in a certain sense we have a restricted framework, you can also very easily incorporate into this framework joint movements of two individuals. As I said here, I have assumed asexual reproduction, but you can also, of course, include joint movements of two individuals, which would simply mean that you have to add another type of transition rates. You can allow for giving birth to twins or three kids and so on and so forth. Yeah? All that could be included here and would only lead to minor changes of the framework. Then you would not only have the next neighbors, but the two next neighbors on the left-hand side, because you can give birth to two individuals. All that is possible. All that is possible. Yeah, but we restrict our attention to a simple example here. N is the maximum population, lambda mu are the birth and death rates. You arrive, if you simply mechanically write it down at this master equation, the inflow of probability to a state N is given by the death, R n minus 1 is, the birth rate given n individuals, and Ln is the death rate. So it's given by the birth rate, if you have n minus 1 individuals, times the probability to have one individual less, so then one more is born, and you enter into state N. Or you have initially one more individual, one dies away, and you enter into N. That's the inflow of probability, and vice versa, you have the outflow of probability. If starting at state N, one more is born or one dies away, then you move into n plus 1 or n minus 1. The first jump moment, to use these concepts, can be easily derived with the definition of it that we have introduced. The movement to the left and to the right is simply a movement by a unit step 1, yeah, one more. N prime minus n, if 1 is born, is 1 times the transition rate, which is Rn. Losing one individual has n prime minus n equal to minus 1 times Ln. And if you insert our hypothesis here, you end up with lambda n minus mu times n squared divided by capital N. In a first order approximation, you get this dynamic law for the mean value of the population size. N is the population size. Yeah. The first order approximation gives you lambda n squared minus mu times n, lambda times n bar minus mu times n bar squared divided by capital N. And this is a very simple equation. It's nonlinear, but it's in closed form, and you can analyze it. And if you look at concentrations, concentrations now would be the population compared to the maximum carrying capacity, capital N, a somewhat different interpretation of our numbers. Concentration in terms of the maximum carrying capacity would give you the master equation here, which looks similar as the ones that we have been looking at before, because now we again have discrete steps in x of 1 over n and minus 1 over n, and then deriving for, which is not a sentiment index, but it's a population density, deriving for the population density, the dynamic law for its mean value gives you lambda x bar minus mu x bar squared. A very simple equation. And in second order approximation, you need the second derivative. Yeah, if we want to implement this one here, you need the second order derivative of the first jump moment. This here is the first jump moment, or say this one is the first jump moment. This is already the first order approximation. The expectation here is the first jump moment, and the second derivative turns out to be minus 2 times mu. So that a better approximation to second order of the mean value would involve the variance of the population density. But again, this is something that is not available, but will be available in a moment. And then you can, that's actually a very dynamic system, you can think about equilibria. You get as a standard equilibrium, that's actually a standard model, lambda over mu, birth over death rate for the population fraction, and lambda over mu times the overall carrying capacity for the population number. And if you simulate the system with particular parameter values, you will see that our theoretical results are borne out. Here I have an overall carrying capacity of 200. I have lambda equal to 1 and mu equal to 2, which leads to an equilibrium of 1/2, yeah, which means 100 agents or 100, I don't know what, sheep whatsoever, whatever the population of our species here is. 100 sheep would be the average expected population number. And you see, if I simulate the system, and I started here with a small number, I just started with 1 or 2 individuals, they will quickly move upward. Yeah, they will reproduce very easily because the death rate is relatively small, and will quickly reach the equilibrium and then show fluctuations around the equilibrium. The equilibrium for the population density given the state-dependent death rate and the constant birth rate. And here you see the dynamic equation. That's just a plot of this first part, yeah, without the influence of sigma x, the first part of the dynamic equation here, the differential equation, and it has its equilibrium. It's increasing here and it's decreasing here, and the equilibrium is at 0.5. So half of the maximum capacity is the attractor for the population size. The only thing that remains is, and we will go back to this example in a moment shortly, the only thing that remains is to see what the influence of sigma x is. Because sigma x apparently has an influence. Yeah? We can understand the system behavior quite well without looking at this additional factor, but we know that allowing for this additional factor gives us a more precise characterization of the mean value dynamics, and we will look at the difference in a moment. The second example, and that is then my major example for social interaction in financial markets or in political systems whatsoever, we have transition rates that are described by these exponential functions. That's motivated both by discrete choice, because in discrete choice you typically have exponential utility functions with stochastic terms, but it's also motivated by statistical physics, where you typically use an exponential ansatz for the transition of particles from one state to another state. But in fact the functional form is not very important. Just for the concreteness, I assume that now we have this self-referential aspect here. Yeah? We have a movement from minus to plus according to this function here, and the movement from plus to minus according to pretty much the same function but with a negative exponent. What does it mean? Now, the higher x, that means if you have a positive majority, the more likely it will be for an individual who has been pessimistic to also join the positive majority. Yeah? These transition rates are increasing in x, and vice versa, of course. The movement in the opposite direction will have a negative dependency on x. Alpha O is something like an autonomous term. If alpha O is positive, it would give you some general preference of the population for the plus opinion. If it is negative, you would have some general preference for the minus opinion. And V is something like the velocity, so to say, of the individuals to switch between opinions. So V just governs the dynamics, the speed of the dynamics of the system. It's relatively unimportant. Alpha 1 could be called the herding intensity. That's the key parameter here. The herding intensity, alpha O, is the bias, and V is the frequency of jumps. Inspiration, as I said, from discrete choice. This is the typical discrete choice probability. If we go back to whiskey, for buying whiskey of, I have no idea of whiskey, so I cannot give you an example. You know the names of whiskey brand A compared to other brands. Here you have brand A, B, and so on. So these are the typical discrete choice, discrete choice probabilities for a consumer choosing a certain brand of whiskey, washing powder, whatsoever. And therefore, this ansatz, so to say, this ansatz has adapted the exponential function that we know from discrete choice, and it's also very often used in magnetization, for example, in particle physics. So there's a certain tradition of using these functional forms, and they have a certain appeal, as we will see in a moment, but it's not really necessary. Just take it as an example here. You can use other functional forms, and in some of my papers you actually see quite different functional forms. So just for the sake of concreteness, we have this exponential dependence on the forcing factors, and the one endogenous forcing factor here is x. So we have a feedback from the overall population composition on individual decisions. And that's the interactive component that was the focus, as I said in the introduction, of my interest. So now we go through that, through the apparatus with these particular transition rates for individuals. Using these transition rates means that I get, for the transition of the population, you have to distinguish between transition rate of the individual and the whole population. the whole population moves upward to one more optimist by multiplying the number of pessimists with the transition rate. And it moves downward by multiplying, or you get the transition rate for moving downward by multiplying n plus with the transition rate for the plus member to move to the minus group. This gives us the first jump moment immediately if we insert into the pertinent formula. And we get this somewhat lengthy expression here. Can be a bit shortened by using the hyperbolic trigonometric functions. E to the x minus or plus e to the minus x can be more compactly written by hyperbolic sine and cosine functions. And using the sine and cosine functions, you can simply look up in a mathematical textbook, you get these expressions here, which look a bit more compact. That's already the first order approximation to the mean value dynamics. Just working through the general apparatus with this particular example. And we can inspect the dynamic properties of the mean value dynamics. And in particular look for stationary states. Since the cosine is positive, stationary states are obtained if the hyperbolic tangents is equal to x bar, so that this is the condition for equilibrium. You get exactly the same condition in discrete choice with social interactions, but there it's static, here it's a dynamic framework. And it's very easy to find out what the properties are. In particular, you get a unique stable steady state x star, say, if alpha O is small and alpha 1 is below a critical value of 1. So if the herding intensity, the interaction intensity is relatively small, but if the interaction intensity increases beyond 1, this formally unique steady state becomes unstable, and you get two more steady states, which I denote by x plus minus star, unequals 0, at least if alpha O is small, which are now majorities that we have seen in the Fokker-Planck simulation before, positive or negative majorities, whereas you get something close to 0 if interaction is relatively weak. You can visualize that in the following way. This is the tangents hyperbolicus for different parameter values. Here I have alpha O equal to 0, alpha 1 equal to 0.8. You only have one intersection at 0. But if alpha 1 increases beyond 1, you have 3 intersections, you get 3 steady states, and the outer ones are, as we will see, stable, and the one in the middle is unstable. And you get some asymmetry here, and that was also the asymmetry that I showed in one of these Fokker-Planck illustrations. You get some asymmetry here if alpha O is unequal 0. And in fact, if alpha O is very high, you come back to a unique equilibrium, because then this bias simply dominates everything else. And here is what I showed you before, namely in terms of the probability distribution, the development of the system that before we have characterized in its mean value dynamics. For particular values of alpha O and alpha 1, here you see symmetry because alpha O is non-existent, and alpha 1 is above 1, which means strong interaction. You get a snowball-like infection of opinions among the population, ending up in a strong optimistic or pessimistic majority, because they have a strong self-referential component in their opinion formation. If you do not have a self-referential component, it would look different. We can do some, in order to, maybe I should come to the end of the first part. we can do some numerical experiments here in order to see how it changes for different values. This is a program for generating this Fokker-Planck equation. Here I have alpha 1 equal to 0.8. So relatively weak interaction. And if we have relatively weak interaction, as our theoretical results indicated, what we get is unimodality. So in contrast to the previous pictures, the most likely observation would still be a balanced disposition among the population, yeah, if they only weakly interact. So the interaction, and that's the basic outcome theoretically of these models, would have to be strong enough. So strong that it is beyond a certain critical value. Only if it is beyond a certain critical value do you have a change of the overall system characteristics. Even if you have social interaction, but the social interaction is relatively small, you have the same result, or in a sense you have a result that is not too different from a system without social interaction. Yeah? Mild social interaction here is relatively harmless. It doesn't change the outcome. You have an expected outcome that is close to what you would get on the basis of only private information, say a balanced disposition among the population. And what you see here is in fact the development of the transient density. What you see here from the back to the front of this three-dimensional plot is here shown in 2 dimensions. The development over time of the transient density, first it is relatively peaked and then it gets broader. It gets broader because of the relaxation of the system, and this is the stationary density. If we use a different value, say 1.2, then we would see how the population, hopefully in a moment, evolves into a bimodal distribution. If the interaction is strong, you have the emergence of these strong positive or negative majorities. Back to our mean value dynamics, the connection between the mean value dynamics and the Fokker-Planck equation is that the mean value dynamics gives you as its equilibria the maxima of the stationary distribution. The maxima of the stationary distribution coincide with the equilibrium values of the mean value dynamics. You see these positive or negative majorities here as the equilibria. If you have strong interaction, you see a balanced disposition as the equilibrium in a deterministic, approximately deterministic system for the mean value dynamics. If you have weak interaction and the values are the same like the modes of the stationary solution of the Fokker-Planck equation. That's the connection between the mean value dynamics, and the probabilistic description. But of course, the probabilistic description gives you more information. It gives you more complete information, whereas you have a very compact and in fact deterministic, which is not true, deterministic representation of the system dynamics in the first order approximation to the mean value dynamics. And as the next step, maybe we should have a break in between, we look at the second order approximation and the influence of volatility on the development of the system, and then we come to financial applications. I think the schedule has a discussion after the first lecture.